Hi, we are Recognai, a small company based in Spain that provides NLP solutions to all kinds of industries. In this video, we will present our work for the ProfNER track in the Social Media Mining for Health Applications workshop. We will start with a quick description of the shared task, focusing on the data and objectives. ProfNER consisted of 10,000 annotated Spanish tweets taken in the context of health-related content, in particular the COVID-19 pandemic. The track was divided into two subtasks. One was trying to predict if a given tweet contained a mention of occupation or not, so basically a binary classification task. The second subtask was to identify those mentions and label them as either work situation or profession, so basically a named entity recognition task. Our contribution to this track consisted of two systems based on neural networks. With System 1, we managed to score highest in both subtasks. Before diving into the architecture of both systems, we will first explain our data preprocessing. In the first step, we extracted the classification label for each tweet and transformed the bread annotations to commonly used IOB tags. Here, we customized a bit the spaCy tokenizer to make sure that word tokens and annotations always aligned well. We did not use any data augmentation or external data, mainly due to time constraints. Now we will have a close look at both system architectures. Both systems share the same basic structure, that is, both have a model backbone and a task head. The decisive difference between the two systems is the corresponding model backbone. In System 1, we used a pre-trained language model based on the transformer architecture. For this backbone, we need to further tokenize our word into subword tokens. In System 2, we concatenate two feature vectors, that is, pre-trained word vectors and pooled character features. These feature vectors are then fed into a GRU that contextualizes the input. In the task head, we solve both subtasks simultaneously. In System 1, we use a special class token to predict the classification label, and we use a simple subword pooling to predict the NER tags. In System 2, we use the last state of an LSTM to predict the classification label and apply a small feedforward before extracting the NER tags. Both systems use a conditional random field in the end to predict a valid sequence of IOB tags. The design of System 1 was driven by trying to maximize the F1 metrics, while System 2 also had in mind the efficiency, that is training, inference speed and model size. In the training process, we focused on the optimization of the training parameters and also the hyperparameters and network architecture in case of System 2. While the optimization of the network weights used a combined loss of both subtasks, for the optimization of the training and hyperparameters, we maximized the F1 metric directly. For System 1, we only optimized the training parameters like batch size and learning rate. For System 2, we also optimize hyperparameters of the architecture. Once we obtained the preferred training and hyperparameters, we performed a quick sweep over several random seeds and used the training and validation set for the final training of our submitted systems. Now the results. As mentioned in the beginning, System 1 was the highest scoring system in both subtasks. System 2, which turned out to be 7 times lighter and faster than System 1, performed significantly worse in comparison, but still scored above average in both subtasks. Our validation and test metrics are compatible, which means that we did not introduce a significant bias towards the validation dataset with our extensive HPOs. The test metrics are a little bit better, which is expected since the final training included more data, that is the training and the validation data. In our HPOs, we also saw a clear positive correlation between the F1 scores of both subtasks, which means that the feedback loop between the two subtasks is working, and we seem to benefit from solving both tasks simultaneously. We conclude that the exploitation of the transfer capabilities of a pre-trained language model and its optimized fine-tuning to the target task provides a conceptually easy system architecture and seems to be the most straightforward method to achieve competitive results. Some possible improvements that were not pursued due to time constraints are fine-tuning the language model on our target domain, trying out bigger or more suitable transformers, or maybe including gazetteers to improve the precision since we always had a slightly better recall. Last but not least, we set up a repo where you can find all our code and are able to reproduce the results. In this repo, you also find a system description with all the details of the two systems. The whole work presented here was done using our open source NLP library, so if you feel like it, please try it out for your next NLP projects. We would really love to receive some feedback from the community. Thank you very much for watching.